So for linear regression, we're evaluating the linear relationship between two or more variables. We're going to talk about two variables, keep it simple. But I'll show you an example of what more than one or more than two variables would look like. And when we're thinking about linear regression, we're thinking about a 2D plot where we have some y or response variable and some x or independent variable. And so in those videos that you watched, they gave some examples of things that people make linear regressions on. So what was an example you remember from the videos? What's that? Femur length and total height. So there was, so we have femur length versus height in humans. Because I also talked about animals too, right? And why would we want to predict height based on femur length? What was the use for that? Forensics, yeah. So you find the body, a skeleton, or maybe anthropology. Is that anthropology? Archaeology? Anybody? It's one of those. I think anthropology is a study of existing humans. Culture, okay. Got it. Okay. So archaeology then. Oh, sorry, okay. So we study people and cultures and people from different time periods, right? So you want to understand how tall they were. So femur length versus total height. And maybe you find a femur. You want to know what the person's height is. Yeah. I don't know geometric similarity.
One of their dimensions is directly proportional, and then you can express the area as functions of those.
Interesting. What did you call that? Geometric similarity. So that, I mean, because this particular example is about geometry, similarity. I bet you there are, forensics and other fields of study that use those principles to relate body parts and sizes. But in this case, we're really not dealing with physical things. We're dealing with statistical relationships and correlation. And so we're kind of taking that. Although, you can obviously use physics first principles, geometry, right, to come up with relationships. So there's other ways to relate a small thing to a big thing, or something that's easy to measure to something that's hard to measure. And that's ultimately what linear regression tries to do. It says, well, maybe we find a femur bone and we want to figure out how tall the person was. Maybe we are suspicious that DDE, which was a pesticide, right, an insecticide, the concentration in bird of prey eggshells. Was it in the eggshells or was it in the birds themselves? The eggshells? Yeah. So they were getting this chemical in their systems, and there's a relationship of this versus eggshell thickness, right? And so that's okay. Behind all of these things are biophysical, physical, electrical, whatever relationships. There's some fundamental process linking A to B, Y to X. Linear regression attempts to find that from a statistical standpoint, but not necessarily, you can't necessarily prove causation. Right? You can't prove that the concentration of DDE is thinning the eggshells, although there's probably some toxicity pathway that a biophysicist or someone could study, a biologist could study and find that mechanism. And I'm sure it's actually been studied because this is, Silent Spring from the 60s. So I'm sure that causal link is well studied. But when we're doing data analysis, often we have these hypotheses and we conduct linear regression to understand initially, is there a correlation? Is there a relationship between something and another thing? So I'm gonna move this over a little bit. So we're getting a little crowded. Okay. And the example I'm going to give is hydrology. That's what I do. So we'll just kind of rephrase this. So y is our response variable. Also known as a dependent variable. X is our predictor variable, also known as the independent variable. And this again gets at, well, there are things that are easy to measure and there are things that are hard to measure. That's one thing we can do for linear regression. So we can measure X to predict Y. Additionally, we are looking for relationships. And so we can measure the concentration of DDE in the eggshells. We can measure the eggshell thickness and then see about what kind of relationship do we have between those two variables. And so you can also use this in a way to evaluate, does a relationship exist? Does the increase in concentration of DDE result in thinner eggshells, right? So there's kind of two things you can do with linear regression. We can use it to predict hard to measure things, and we can use it to study relation between two or more variables. Okay. So I'm actually just going to move down here so we can continue this example. In the field of hydrology, there's a lot of things that are easy to measure that correlates to things that are harder to measure. So in this case, I'm going to talk about what's called snow water equivalence. It's been in the paper a little bit. And snow water equivalence, we measure it in depth, so I'll just write it inches, and it's also abbreviated as SWE, S-W-E. And what that can predict is runoff volume. So how much water comes off of a mountain or watershed with units of, say, million acre feet, which we've introduced previously. And actually, I think this in the video they use an example from Colorado. Was that in these videos or was it in the next one? It was in this video. So they actually had kiloacre feet, and I think I'm going to give you the actual equation they had. So there was a pretty good linear relationship. There's scatter, right? So you can imagine that each of these dots is some measurement of SWE, which you would just go up into a mountain, and obviously you have to do this at a point, and we know that snow depth is variable across the whole mountain, but regardless, maybe this is an average of a bunch of measurements or something. Let's see if we can do that a little bit better. So for a given snow water equivalent, we'll just say xi, we can go to yi, right? And these are just data pairs. So we had some measurement xi, and then we had some observation of runoff. of water flowing past a stream gauge, right? So say we're talking about the Colorado River Basin. There's dozens of these stations that measure SWE, and it's really just the density of the snow, right? And if you know the density and the depth of the snow, then you can back calculate how much water, if you were to melt it all, you have in that snowpack, right, in terms of depth. So I have 6 feet of snow and the density is 30%, and I have 1.8 feet of water, is that right? Something like that. So that's how it works. So we can have these observations, say we have 50 of them over the last 50 years, and there's this relationship. We can plot a line through that, through linear regression, which we'll talk about. And what this line says is, this is y is equal to, there's different symbologies, but I'm going to just do this alpha plus beta x. So y is equal to mx plus b in this case. We have the slope. And we have the intercept. And of course, you'd imagine that if we have 0 SWE, we should have 0 runoff, right? But we're never going to measure 0 SWE. And so we don't necessarily care about what happens when x is equal to 0, right? So we don't, there are some cases where you can force this line to go through the intercept, because from a physically based standpoint, you want to do that. But in this case, you would say, okay, here's the relationship, the linear relationship between SWE and runoff. And we're going to only evaluate it within these bounds, right, of x. So in this case, the regression equation is, we'll say applicable is probably a better word for that. Valid. Say, 1 and 12 or something. I don't know, there's some range, right? Because it's based on your data. And a linear regression equation is really only valid for the range of data that you have. If my observation stopped at 12 inches, do I know that this is linear? Does it extend in a linear fashion? Similarly, does it extend in a linear fashion on this side, right? We don't know. It might not. There might be some non-linearity, right? And I think Carrie talks about this in some of her stuff. There's these kind of regions where the concentration of bacteria over time is log linear, right? So there's times and regions where things are valid. And in this case, it's really only valid within the span of your data. We can make extrapolations, but there's a big uncertainty here because we just don't know. So that's an important thing. So here we go, alpha and beta, and this is the two parameters, right? These are your linear regression parameters. And these are the things that we want to know, and they tell us information, right? So beta tells us that, and I think in this case, the equation, I'll just write out the example. So we'll say y is equal to 1 plus 2 times SWE in inches. So if this is my linear regression equation, beta is equal to, that's my slope. How can I interpret this equation? If I say for every additional inch of SWE that I measure, that results in what? So if my slope is 2, then it's just 2 times, right? So then for every we can expect how many kiloacre feet? And that's kind of the basic thing, right? That's really what it's telling us. For the peregrine falcon example, or the falcon example, is like for every increase in, I don't know what the concentration units are, but parts per million of DDE, we expect eggshell fitness to reduce by whatever fraction of a millimeter, right? So that's one of the outputs we can have. That's the kind of studying the relationship part. Is what is the relationship between X and Y, and why? How think about this equation? We could also think about this in the predictive sense. For this example, I can measure snow water equivalent right now here, and obviously it's going to change from month to month, and it's melting right now. But if I pick this point, I say, okay, peak SWE occurs in March, and I'm going to do that regression with runoff volume. So I could use this in a very kind of simplistic manner to say, well, my peak SWE is 5 inches, so I expect to see 10,000 kiloacre feet to come out of this basin. And that's a predictive tool because I can measure that in March, and then if I'm a water manager, I can go out and figure out how much water I'm going to have to divide up, right? We have to meet this water rate and this water rate, and we have to send so much down the river to Lake Powell. So this is a very simplistic thing. Obviously, there's more complex tools out there. Okay, so that's linear regression. And actually, sorry, let me a couple more points I want to make here. Is that when we look at this scatter of data, we can look at that and say that we see a positive linear relationship between SWE and runoff. And from this, we can say that we have a positive correlation. And we'll get into correlation in the next lecture. And for linear regression to work, we need to have a linear relationship, meaning this equation can roughly define it, A plus BX. So the next part of linear regression is we can actually do multiple linear regression. We're going to just introduce the concept. And in this case, again, we still need a linear relationship. Between our predictor variables and our dependent, still one dependent variable. So we could, if you looked at snow water equivalent, we're like, yeah, that's important. Obviously, that's the water, right? But we could think of a number of other factors, and when you take hydrology with me, this will be more intuitive. But we could say runoff is not just a function of SWE, but we could actually get a better prediction of runoff if we think about some other variables. So we could say we'll throw in SWE in there. We'll look at the average temp, I don't know, from the previous summer, right? How hot was the last summer? That dries the soil out. If the soil is really dry, then it's going to be more thirsty, right? When the snow melts, some of it's going to go into the soil. We could look at soil moisture metrics. Maybe those are cross-correlated. We could look at elevation, like average elevation in the basin. There's a ton of things that we could do and measure ahead of time that would allow us to predict what the runoff is. And all of these things might share some predictive power for runoff. And so in this case now we say runoff is equal to some intercept plus beta 1 times SWE. Maybe that's the most important one, plus beta 2 times temp plus beta 3 times moisture, and so forth, right? So each of these coefficients represents a slope, right? How much, and you can think of that as like the strength of the predictor variable. So if SWE, if that beta is 2, then maybe temp is not as strong as a predictor. And so maybe that's somewhere around 1.3, and soil moisture is a little bit less strong, and so that's 0.7. And so, and obviously these coefficients are going to be tied to the units, right? So if I do Fahrenheit versus Celsius, I'm going to have a different beta value because the units are really important. So that's what a multiple linear regression would look like, and it'll tell you, we'll get into like interpreting statistics and stuff, but it'll actually tell you if this coefficient is statistically significant. And then the last type of regression that I'll talk about, there's a bazillion of them, but is nonlinear regression. And if we have some data and we see some nonlinearity in that, right? And you guys do this in Excel all the time, right? You got a scatter plot, you fit an equation, and you can just keep adding polynomials to it, right? And eventually it'll create something that'll fit. That's nonlinear regression. It's fitting some nonlinear equation to the line. And this could be a number of things. The ones I'm familiar with are peak discharge, say in cubic feet per second, drainage area, say in miles squared. And this is often a power law kind of relationship. So Q peak is equal to alpha Q to the beta. Sorry, alpha drainage area to the beta. So with nonlinear regression, it's different techniques, different statistics, and just a whole other way to interpret the results, right? So we're gonna pass on that for now, but this is often used in engineering applications because we have a lot of nonlinear relationships. A lot of the design equations we use are based on experimental data fit to nonlinear regression equations. Back in the day when they didn't have R to do it, and so some of those regressions probably are a little suspect. That's another story for another time. So let's get into a little bit about the theory behind linear regression. And then I'll introduce what kind of some of the statistics that we can do with it. So if we go to back to a basic plot, and I'm going to draw it this way because we could have a positive or a negative correlation. here are my data pairs. Here's my regression line that fits the data. And we're kind of going to look in at some of these actual data points, right? So if I've got my individual data points, and then I have the regression line. And what this regression line actually represents is a mean response. And so that would actually be the kind of given a value of x, what is the mean response I would predict based on this relationship. So if this is my xi that I plug in, then I'm going to get out some average response. You can see, like, if there's a big scatter here, so I'm really looking at the average output that I would expect. So that's, we're going to call that y bar for the mean response. And if I take a slice, I'm just going to do this in green. If I take a slice at any particular x value, I can expect to see a distribution of potential responses. Now, I'm not going to have a bunch of points fall on that line, but there's a general scatter about the line, and you could think of that as either a histogram or a distribution, right? Ideally, a normal distribution, meaning that I have symmetrical scatter around the regression line. Also known as residuals. So residuals are the difference between an individual data point and that line. And so this is what we'll call the residual error. And that's evaluated for an individual data point. So residuals are really just the error or the difference, and we can do some summarization, you know, kind of like a variance, right? How far are our observations taken as a whole from this regression line? And we can think about this probabilistically. That the expected value of y at some value of xi, which is that regression line. I'll just write that out. So this expected value of y given x is equal to xi is equal to alpha plus beta xi. If we write it out as alpha and beta, then these are what we could think of as population parameters, meaning the true underlying relationship between x and y are alpha and beta, and we're going to estimate those using this hat nomenclature. So y hat is equal to alpha hat plus beta hat x. And these are from our sample. So our sample estimates. So anytime we do a linear regression, we're estimating alpha hat and beta hat. Or that's what we're coming up with based on our data, and those are estimates of the true quote unquote population parameters. Now, the standard method for doing a linear regression is what's called least squares regression. Sometimes we tack on an ordinary, often abbreviated as OLS regression, ordinary least squares regression. And it's a very straightforward formula to estimate those parameters. Given a series of paired data, beta hat is equal to the sum of the differences between the individual observations and the mean times for X and for Y, divided by the squares of the X's, the differences of the X's. And this, of course, gives us our slope. And then alpha hat we can solve by the linear, just the line equation. So we solve for the intercept by plugging in two numbers that we know pass through the line. And those two numbers happen to be y bar and x bar. So minus beta x bar. So what this tells us is that the regression line always passes through x bar, y bar. So the mean of your x's and the mean of your y's, that's going to be on your regression line. So let's talk about the key assumptions that go into linear regression and how we do confidence intervals or bands for linear regression. We'll take a few-minute break and then we'll do this in R together. I'm just giving you this equation because it's what's used. We're probably never going to do this by hand. So just know that it's not that complicated. And it's based on all of your data, right? So all the X's, all the Y's, Y bar, X bar. And that's what allows us to do that least squares regression. So it's a real quick calculation. Okay, the first assumption, and when I say assumption, is these should be met or pretty close for this statistical analysis to be valid. And we'll get to explore that together. So the first one is called constant variance of residuals. This is also known as, and this is a mouthful, homoscedasticity, as opposed to heteroscedasticity, right? So homoscedasticity means that we have a constant variance of residuals. What does that look like? If this is my linear regression, then I want that spread to be roughly equal across the whole series of data. And I'll show you some examples of when it might not be. So the residual, again, is just the difference between our individual observations in your regression line. And we can then plot that. It's basically if you detrend the data, if you take the slope out of the data, you can plot your residuals, and R has a nice tool to do that. So we still have X, and in this case, we have R for residual. So now the slope is gone, and we're just looking at the spread of our data. And you want to make sure that it's fairly even, right? You don't want to see something like this where, and I'll just show you another example. And I'll just say this is homoskedastic. So if we had something like this, let me see. I'm not going to necessarily draw it perfectly, but say we had really big scatter for low values of X, and then a little bit of scatter here, and then some more scatter here, something like that. We drew our line through there. And then we looked at a residual plot. And maybe the residuals are like kind of really extreme here, but they're funneling here, and then maybe they get more extreme out here. You can have all kinds of different shapes. Maybe you have residuals that follow a trend like, that's kind of like a, I don't know what that is. U-shaped. We could have residuals that, you know, kind of follow some nonlinear thing, right? Like there's a lot of different ways this could come out and look. And this is what's called heteroskedastic. And a lot of the assumptions and tests we do don't work if this is the case. So you want to have a roughly even distribution. This is mostly a visual assessment. And a linear kind of spread for low to high values, right, of X. The second assumption, and I should say that this is all based on, we plotted the data, and it looks like there's a roughly linear relationship, right? That's the kind of the first thing. Okay. The second is that the residuals are normally distributed. And if I go back here, and I were to take a slice across here, and I look at the spread of my residuals, you know, for a given slice of X, are they normally distributed for that X? And a lot of the tests and stuff we do assume that, in fact, they are, and they're symmetrical, right? And what's a good way for actually testing if something is normally distributed? And we did this for our distribution fitting discussion. Yeah, do you remember the name of those kinds of plots? QQ plots. So we have our Q theoretical and our Q observed, and they should follow some kind of, this isn't linear regression, and I shouldn't have drawn it as a scatter because these are all ordered. They're not going to overlap. You can do a QQ plot for your residuals. And so this is called a QQ plot. And in R, you would just do QQ norm, whatever object your residuals is stored in. So you can, and we'll look at this, you can extract your residuals from the linear regression, plug it into QQ norm, and it'll create a plot for you. So that'll give you a good idea if you're normally distributed or not. The last key assumption is that our linear regression model, and this is a model, right? It's an equation that we use to predict things. So our linear regression model is valid over a range of data. And usually we think about this as our X values. And so we talked about this here earlier, right? We have that regression between snow water equivalents and runoff, and we made that between, say, 1 and 12 inches, and then it's valid for that. We can always collect more data and extend it and rerun the analysis, but until we do that, we shouldn't make predictions beyond the range of our data, because it is an unknown. Okay, so let's take a few minute break, and we'll pull up some R and we'll kind of go through that R markdown document. I've posted this R markdown document, and I've also posted the data set for this on campus. So if you go to modules, week 14, and under linear regression in R, I've got some information here. So here's the R markdown notebook. So it's a PDF. The fish data, it's a CSV. I also posted a video of me going over everything. It's about a 10-minute video. So kind of step by step in R. So you can always go back and interpret that or look at that. Okay, so I'm going to just go through this PDF a little bit just to introduce you, and then you'll actually do this for the second part of the project. So we don't have any homework or anything associated with this. It's just going to be in the project, because you can only do so much. So here is this example. We're looking at the relationship between mercury concentration, and that is micrograms per gram. So micrograms of mercury per gram of fish tissue as a function of the fish length. And I think this is for a certain species, or maybe it's a kind of just predatory fish. It looks like largemouth bass caught in a certain lake in California, Lake Natoma. Anyone been there? I have no idea where it is. I should look it up. Unfortunately, this mercury in fish tissue exists in most fish anywhere in the world because of, does anyone know where the mercury comes from?
Isn't there like a baseline level? And then anything that has it that gets eaten gets added to whatever eats it?
Yeah, but how does the mercury, and that's a good point. We'll talk about how does the mercury get into the ecosystem in the first place? From coal, from burning coal. That's the biggest source. I think there's a lot of other sources out there, but really burning coal, and that typically releases it into the atmosphere. It precipitates down. It gets into everything. And then Kenneth's point is that predatory fish, they eat fish, right? Who eat bugs, that eat algae. And so as you go up in the food chain, you bioaccumulate or concentrate the mercury. And so by the time you get to a predatory fish species, you get really high concentrations of mercury in the tissue. And then humans, of course, on top of that food chain, can get mercury poisoning or high levels of mercury in their system by consuming a lot of fish. Fish is good for you, but not too much. So that's just a little bit of background there. And here's where they caught these fish, measured their length, and then took a biopsy, a flesh sample. I don't know if they killed them or not, but it's bass, whatever. There's a lot of bass out there. And measured the mercury using a mass spectrometer or something like that. So you can go, I kind of give you just some more background of that. Here's how I plotted the data. Just plot, right? The fish data is set up, I think there's just 2 columns in it. And I set it up so that the first column is the length and the second column is the concentration. So If you tell R to plot a data frame with 2 columns in it, it'll give you something that works. The next thing we can do is look at the correlation, and we'll talk about this next time, but there's a function, it's just core, C-O-R. You put in the data, there's different methods to calculate correlation, and it'll tell you the correlation of every variable with itself. So if you have a data frame with 6 different variables, it'll tell you the correlation of each variable compared to all the other ones, right? And in this case, there's only 2 variables, so it says the length correlation with itself is 1, it's perfect. It's a perfect fit. So correlation of 1 is a perfect positive fit. Correlation of -1 is a perfect negative fit. And we'll get into correlation in our next lecture. And then the correlation between concentration and length is 0.85. So we'll say we can interpret that in a little bit, but clearly it's a relatively strong correlation. It's close to 1. There's a lot of ways we can interpret that from a numerical standpoint, a quantitative standpoint. Let's look at how we actually do the linear regression model. So we're going to do ordinary least squares. And in this data frame, I've got names for the 2 columns. So the length column is called length, the concentration column is called concentration, C-O-N-C. There's a lot of ways to input this. I'm just showing you the basic way. And we'll use a function called LM for linear model. So LM. And I'm saying concentration, tilde, so that's a little squiggly, tilde symbol on the top left of your keyboard. So concentration, and this just means follows, or is a function of. So concentration follows length. And then I say, well, how does it know where these names come from? Well, this is the data we're using. So data equals fish. Fish is the data frame that has these 2 columns in. So concentration is my dependent variable. This is my independent variable. And I'm storing that in this object fit. So fit will just store it. Nothing will happen. You won't see anything. There's no blinking lights or bells or whistles. But we'll get to that. We'll get some bells and whistles in a second. So now I can actually, okay, I did that linear regression. I can plot it. And I went ahead and plotted the scatter plot. So plot fish, that's my scatter plot. And then I use this function, which you may have used before, AB line. So AB line just refers to A intercept B slope, right? Y is equal to A plus B times X, or MX. Anyway, yeah, so Y is equal to A plus BX, where B is the slope, A is the intercept. So that's what AB line is. And if you feed it the coefficients, so there's another function in here, coef. If I feed it the coefficients from my linear fit model right here, so fit contains the model, coefficients extracts those 2 coefficients, A and B, and then I plug that into AB line. So it'll plot a line across those data. So that's my linear regression model. Note that AB line will plot it from 0 to infinity. So it won't stop at your data points, like the range of your data. It's just something to remember. Now we can actually look at what's inside of our model. So this function summary, I do summary fit, fit contains the model, and then it gives me a big summary of everything that's in there. So it repeats the formula. So this is the linear regression model, concentration follows length, or concentration is a function of length. It gives you some information about your residuals. The median residual is -0.01 or 0.001. The max residual is 0.15. So some estimate of your scatter. And then it gives you some actual statistical results relating to the intercept, which is just A. And then it says length. So length is just the one variable that we're actually looking for a regression of. In this case, length refers to the slope or the B coefficient. If you're doing multiple linear regression, there might be length and then weight and then age or something like that, right? So you could have many variables. Each one of those represents a slope term or a beta. The estimate is the value itself. So this is beta hat. For the intercept, this is alpha hat. It gives you the standard error. So this is some indication of the uncertainty of that variable, right? It's an estimate. Just like X bar, the mean of a sample has a 95% confidence interval. So do these parameters. These parameters have t-scores based on the data, the amount of data you have, right? And we'll look at what that t-score equation is in the next lecture, but you actually have a t-score for these particular things. And then you've got a p-value, the probability that you're greater than the absolute value of t. So this is the area under the t distribution to one side or the other of these t values. And so these stars mean you're significant, right? So if you get 2 stars, you're significant at this level. This is a 99% level. 1 star is the 95% level. 3 stars is the 0.999% level. It's not hard to get, with linear regression, it's not hard to get statistically significant coefficients, length and intercept, or intercept and slope. So that just means that your coefficients are legit. You do have a significantly significant positive slope, right? Meaning the slope, sorry, I'll ask you, what would the null hypothesis be for a slope coefficient? So when you think about a null hypothesis for mean, what's the null hypothesis for mean? We can think of this as a one sample test. Yeah, there's no difference, right? The mean is not different from the population mean that you're testing it against. In this case, what would our null hypothesis be? The slope is not different from 0. If there was a 0 slope, there wouldn't be there would be a flat relationship, right? That's not really a predictive relationship. You're just saying that y is equal to the mean of x, or x is equal to the mean of y. Anyway, so there's no slope. There's no more information than just a flat line or an average. So the model would just be y bar. So this says that we have a slope that is statistically significantly different from 0. It's a tiny slope, right? But these, again, are tied to the units. So the micrograms per gram per millimeter of fish. We've got a bunch of other things here that we'll get into in the next lecture. But R squared values are really important. And this tells us the percent of variability of y that is predicted by x. I'll talk about that more next time. But if I say I want to do the linear regression between fish length and mercury concentration, well, in this case, about 70% of this variability, you can still see there's variability, right? But 70% of our ability to predict mercury concentrations is predicted by the length. There's some other scatter and noise out there. Maybe there's some other variables we could bring in to cover that variability, but length covers a lot of that. It does a 70% job of predicting y, basically. So I go in and really get into all of the different outputs and describe those in more detail. The last thing I'll say before we just call it is this F statistic. And this relates to the overall model. Is this model a significant model or not? And in this case, the null hypothesis is that X And y is just, it's just flat, right? There's no slope. It's really just the mean. We could just take the average of y, and that would be our model as a function of x. And so this F statistics is our model. A legit model is a significant model. We won't have time to actually get into how this test is done, but it's another diagnostic you can use to evaluate the model itself. So next time we will, actually no, we've got 3 more minutes. So I'll just talk about this really quickly. We can check our linear regression model assumptions. And if we use the function residuals, that'll extrapolate the residuals, which is just for a given XY pair, what is the difference between that and your linear regression line, vertical distance. So if I extract the residuals out and put it in this object R for residuals, and then I can just do QQ norm and QQ line and do a quantile plot. And if my residuals are normally distributed, then they should fall closely to this line. If they're not, you'll see some weird pattern. I can plot my residuals, and you might want to zoom out just to see, okay, here's 0. This is my regression line, flat, right? And then you can see there's not any necessarily wild pattern in my residuals. They're all pretty evenly distributed. I don't have a big cluster that's wider here and narrower here. I don't have some weird nonlinear shape in my residuals. And then I've got, I'll just read this and we'll be done. We can report our findings. So in this case, we're saying the mercury concentration in tissues sampled from 20 largemouth bass is positively correlated to fish length. And I show my correlation coefficient. I denote it as rho. A linear regression model between fish length as an independent variable and mercury tissue as the dependent variable is significantly different from the null model, which is that it's all just that averages are the only relationship there. And here's my F test, and my p-value is less than 0.05. The slope of this relationship is 0.0032, meaning that for every centimeter of fish tissue, so I'm multiplying because our data was originally in millimeters, mercury concentration is predicted to increase by 0.03 micrograms per gram in fish tissue. The slope is significantly different from 0, and here's the test statistics. So that's a very thorough way of reporting a very simple linear regression model. So next time we'll talk about a little bit more about this kind of statistics of linear regression, and then we'll introduce confidence and prediction intervals, which gives us the uncertainty around our linear regression model. And this is what they look like. I'll just leave that up for your visual entertainment.